Hello everybody, my name is Ben and welcome to Math with Ben, and today I would like to talk to you about the concept of limits. This is the first of a series that is an introduction to calculus and sort of a fun way of, energetic way of sort of representing what calculus is to people who may not be as interested in math, or people who want to get into math, or people who just don't know some calculus and want to learn it, and I will be, doing my best to help them with that. So we have this idea of a limit, right? What is a limit? Well, a limit is an operator. You've experienced operators in mathematics before, such as the basic arithmetic operators, which is, addition, subtraction, multiplication, and division, right? These are the basic arithmetic operators. And what they do is they sort of, they add, subtract, they change numbers, right? They take numbers and they change them. Not in a literal sense where they take one number and change it into something else. They take multiple numbers or more than multiple, like a ton of numbers, and what they do is they just change them, right? Using other numbers. So if you take 3, you can change what 3 is by taking one of these operators and another number and using them together, right? If we want to change 3 into 6, all we have to do is multiply by 2, and that is equal to 6, right? This is an operation. We just used an operator on a number to get a new number, right? And we can apply a similar concept to functions. If we have one function, say g of x, and we want to change it in some way, say we want to scale it, as in multiply it by some constant, we can do that, right? If we want to take g of x and scale it by a factor of 2, all we have to do is multiply it by 2, and we can get 2g of x. Say g of x is equal to x cubed, well then 2g of x is equal to 2x cubed. Right? It's just the idea of changing a function or a number in some way using one of these operators and operating on the actual function or number. And so we can expand our knowledge of what operators are by adding more, right? So we have this idea of a limit. A limit is, of course, an operator, like I already said. And what it does is it doesn't change much in any way. It just sort of differs the thinking of what you do when you're using a function. So if we have the function, right, f of x is equal to 2x squared. We can graph this, of course. And I know it's not an amazing graph, whatever, right? And this is the graph of 2x squared. What a limit does, if we take, say, the limit denoted by sort of a cursive, it can be non-cursive if you wanted to, sort of however you write, really. We take the limit of 2x squared, so lim 2x squared. As x approaches that some arbitrary value, you can decide, or whatever problem you're given can decide, and you sort of have to determine what the limit of 2x squared is at that value. Say we want to find the limit of 2x squared as x approaches 3. How can we do this? Well, we can start by thinking about what 2x squared, or f of 3, 2x squared at 3, f of 3 might be. So if we plug in 3, if we have f of 3 is 2 times 3 squared, right? That's just how you find a dependent variable, f of x, when you have an independent value, which is 3 in this case. It's the value for the independent variable for x. So we have this, right? And this is, of course, equal to 18, right? 9 times 2. 3 squared times 2. 3 squared is 9 times 2 is 18. And so what is the limit of x equals 3? Well, in this case, it's 18. How did I know that? Well, I know that f of 3 is 18. So all the limit is saying is, as you get closer and closer and closer to some arbitrary value, whatever it might be, what is the value of your dependent variable, right? And of course, in most cases where a function is what's called continuous, I'll define that in a second, you can just plug x straight into whatever function you have, or you can plug the value into whatever function you have, and you can get out the value, right? In some cases, that's not true. So let's take a look at... So let's really dive deeper into the idea of a continuous function. So what is the definition? Well, we have our definition here, and the definition of a continuous function is a continuous function is a function who has no holes, wrong hole, no holes, no jumps, and no vertical asymptotes. A continuous function is a function who has no holes, jumps, and no vertical asymptotes in its graph. So let's take a look at some examples and see whether or not they are continuous. We have like a graph of like sine, whatever. That's not perfect, but it doesn't really matter. We have a graph of the absolute value of that. Like, let's say absolute value of x, and we have one more that looks something like this. Well, let's guess. Is this first one continuous or discontinuous? That's right, it's continuous. There are no holes, there are no jumps, and there are no vertical asymptotes. Is this second one continuous? That's correct, it is continuous. For those math nerds who already know calculus, it is not differentiable, but it is continuous. This third one, is it continuous or discontinuous? Right, obviously it is discontinuous. We have obvious jumps, we have obvious holes, vertical asymptote, right? It violates every rule on the planet Earth. So let's take a look, right? We have this middle function here, which I said was the absolute value of x. F of x is equal to the absolute value of x. Let's graph it a little better. Right, and this function is the absolute value of x. Well, we really want to get this idea of a limit down. So the limit, what is the limit as x approaches 0? The absolute value of x. The reason I choose 0 is because it looks a little funky, right? Absolute value of x is taking us to Funky Town. We see here at where, the origin 0, 0, that there's like this really, 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 really sharp point, and it looks a little odd, and it could get in the territory of feeling discontinuous. So we want to know whether it's continuous there or not. How can we do that? Well, we can take the limit from the left-hand side of the graph, left-hand side of 0, and we can take the limit up from the right-hand side of 0, and if they agree on what the value is approaching at that point, then the graph is continuous. For most cases. There are some, that's not true. Most cases, right? So why don't we start by taking this limit as x approaches 0 from the left. Let's create a little chart here. We have our x value and we have our absolute value of x here. So if we do -1, well, we're going to get at 1. If we do -0.5, we're going to get 0.5. And if we do -0.01, we're going to get 0.01. And you can see, right, as we get smaller and smaller values for our independent variable, our dependent variable, which is the function, the absolute value of x, approaches 0. It gets closer and closer to 0. So we say that the limit of the absolute value of x as x approaches 0 from the left is equal to 0. And that's amazing. That's amazing. Now, all we have to do to, again, check if it's continuous or not is take that same exact limit, x approaches 0, from the right. And if they agree, this function is most likely continuous. Again, there are some cases that's not true, and I can talk about those later, but for now we're going to talk about cases where it is true, such as the absolute value of x. So we again can create our chart here, x, absolute value of x. And then, why don't we plug in some similar values, right? 1, we get 1, 0.5, we get 0.5, 0.001, 0.01, we get 0.01. What the heck? They agree! This is incredible news. This means that the function f of x equals the absolute value of x is continuous. This limit is also equal to 0. Whoa! That's insane. This is incredible news. This means, again, like I just said, that the function f of x equals absolute value of x as x approaches 0 is continuous because the limits agree. You know, they're not actually agreeing, but they say the same thing, so let's take a look at another case. Why don't we do an interesting function? How about we take the function f of x is equal to 1 over x. Let's graph this out. Well, I already know what this graph looks like. This will be, if you're a math student or you're interested in math or you want to become interested in math, this is a graph that you'll just memorize over time. Well, first of all, you can see straight from the bat, vertical asymptote. Huge red line right here. It is not continuous. You can see that, obviously. Let's prove it. Let's prove it. Not doing an actual proof. I'll talk about proofs later. I love proofs so much. But anyway, let's start. Well, like I did earlier, here in this polynomial somewhere, here, I just plugged in 3. So, let's start by trying to plug in 0 to this function. We get, right, f of 0 is equal to 1 over 0, and that's equal to... Wait. You can't do that. That is a felony offense up to 10 years in federal prison if you divide by 0 in math. You can't do it. You can't. So how then do we find what the value of this graph approaches as x approaches 0? That's right, we take the limit. You are a genius. Limit as x approaches 0, let's start from the left again, of 1 over x is equal to what? Oops. Well, let's again create our little chart that we had. X, 1 over x. If we do 1, then this is 1. If we do 0.1, this is 10. If we do... Oh, I'm approaching from the left, so all these are negative. Sorry. If we do negative 0.01, we get negative 100, and yada, yada, yada. This number will get bigger and bigger and bigger and bigger and bigger until you reach infinity, which you will never do. You can't reach infinity. It's impossible. But what you can do is get close to infinity. Not really, but you can approach infinity. In math, in general, when you have a fraction, the numerator, whatever it may be, the denominator is the more important part. You know, every number in math is important. But the denominator is more important because it determines what a function does and how it acts. If your denominator is getting bigger, or if your denominator is getting smaller and smaller and smaller, your fraction will increase a higher and higher value because you're dividing by lower and lower numbers, right? If you divide 1 by 1, you're going to get 1. But if you divide 1 by 0.1, you're going to get 10. And this trend continues. The trend continues, right? So what if we have the ultimate lowest value, 0, right? You can't get smaller than value. You can get negative, but you can't get a lower value than 0. Well, this function will approach infinity. In this case, negative infinity, right, as you can see from it going downwards. And that's okay. That's perfectly fine. A limit can equal negative infinity. That's okay. So, do our functions agree? I think we can already determine that it's not continuous, 1, because I already said so, and 2, because if you get an infinite value as the limit of some function, there's most likely, or always, an asymptote, a vertical asymptote. It's pretty much always true. I think it is always true. I don't know. Please fact check me. I would love if you fact checked me and told me if I was wrong in the comments. That would be amazing. Because I learned too. So what is this? Well, I'm sure you can guess that it's positive infinity, but let's show it. It's important when we're doing math to actually show things. You might say, well, I can know that one thing is true, and I can tell you that it's true. Why must I also show that it's true? I don't know. Mathematicians think it's important, so you gotta do it. Anyway, if we have 1, we get 1, right? We're just gonna put in the same values, but, different sign because we're approaching from the right this time. And we can see, again, it follows the same trend, but opposite, so it's going to go towards positive infinity. So this function discontinuous. And that's all that I have for you today. If you would like me to post some practice problems to some page, I might create an Instagram account for this channel. If you would like me to post practice problems anywhere, please let me know and I can do that, and I can post answers and whatever. If you need help, you need help. So that's all I have for you today. Thank you for watching. I am Ben, and this has been Math with Ben, and I hope to see you next time where we talk about derivatives. Thank you and have a good night.